Hello, everybody, and welcome back to the show. My guest today is Jeff Orchard. He's an associate professor and director of the Neurocognitive Computing Lab at the University of Waterloo. The human brain is one of evolution's greatest creations, yet we know shockingly little about it. Fortunately, Jeff is working on better understanding the brain through artificial intelligence systems. Expect to learn why you may have learned to be bad at math, why our brains ballooned in size, how dolphins may be smarter than us, Jeff's predictions on when we may achieve artificial general intelligence, how AI might make another massive leap soon, and much more. You may be watching but not subscribed, and that makes me very sad. To fix that, please click subscribe below if you're watching on YouTube, or go to the podcast homepage on Apple Podcasts or Spotify and click the plus follow button to not miss the next show. I thank you. But now, ladies and gentlemen, Jeff Orchard. What is a brain and what do brains do?
Well, I guess everything, the brain is part of the central nervous system. And the central nervous system is basically what all animals have. And its job is, plants don't have brains. Why? Because they stay put, they just soak up the sun. They don't really do any actions. Animals come from the same root as animate, because they move. And a brain is basically a computing device that takes information from the environment and decides what actions to do. Because as soon as you can move, you have to decide what moves to do. So it doesn't sound very romantic, but brain is basically a mapping from external stimulus to what action should I do. Now, that can be extremely complicated. Not that for some animals, it's not that complicated. Like they just have to find the food and go get it, eat the plants or whatever, and try to not get eaten themselves. When you get into species that are social, then it becomes like for humans and lots of other species too, a lot of our adaptations and our sort of skills come from our cooperation. So a lot of our brains, one could argue, are devoted to social engineering and solving problems in groups and maintaining relationships and knowing how to manage in a setting where there are a whole bunch of other agents that you kind of depend on. So that makes the mapping from sensory environment to what to do a lot more complicated. That's why one could argue that's why we have bigger brains.
Gotcha. And this is almost going back to the Dunbar's number, which I believe is 152 or something like that, which takes advantage of the theory of mind concept. So this is not just thinking, okay, what does Sally think of me and what does Mike think of me? But you need to think, okay, what does Sally think of Mike? So I know how to operate in my environment. And then, of course, you add more nodes, more people into that environment, and that becomes exponentially more complex as you entertain that.
Yeah, I guess technically it's quadratically more complex, but that's good enough. That makes
Thank
it
you
hard.
for the correction. I studied engineering. This is kind of embarrassing. So with that concept too of learning from your environment, taking stimulus and cues from your environment, and then doing things, that's a lot like algorithms and software. So could you kind of explain a little bit of what an algorithm is for people who are unaware, just a very top line level, and then how can we better understand the brain by understanding algorithms?
Sure. An algorithm is basically a recipe to solve a problem. So you've got, usually it's a number of steps of, you take some information that you sort of enter into this algorithm and you follow the steps according to what the recipe says. And by the end of it, hopefully the problem that you were aiming to solve is solved. And if it truly is an algorithm, the problem should be solved. There are algorithms that are, I guess, technically not algorithms. They're more heuristic algorithms where there are guidelines for things to do that will give you a decent solution, but not necessarily give you the optimal solution. So was that a compound question? Was there a follow-on to that? I can't remember.
Yeah. So that's kind of the high level of what an algorithm is. Also, too, heuristic is kind of like, we don't have an exact solution, but this kind of fits into this bucket. So let's go down this path just to make sure that's correct. Yeah. Part two of that was, what can we learn about ourselves, about the brain, by studying algorithms and understanding them at a deeper level?
I guess what the brain, if you accept the concept that the brain is a computing machine, which I think scientifically is pretty well established, then it's basically computing algorithms. It's the computation it does. It'd be nice if we could understand it in terms of algorithms. So we have a bunch of algorithms. We as a society, as a human race, have a bunch of algorithms that we apply to different problems, signal processing, like your MP3 players, or I guess it's not MP3 anymore, but all these different things, image processing, how the internet works, they're all algorithms. It'd be nice if we could figure out which of those are being used in the brain, or which things that the brain is doing are common, or what commonalities there are with the algorithms that we already know and use. And there seem to be quite a few recognizable algorithmic sort of things that are happening in the brain. It's not just this completely random mix of neurons. There seem to be some conceptually recognizable solutions in there. But still, most of it's kind of not understood very well, and we're still trying to unpack it and figure out what it's doing.
You mentioned signal processing, which I think is a very interesting topic, not only just because of how magical it is that it enables us to do so many things like wireless communications and stream, hopefully, this podcast to someone's phone and then into their ears. But also, when you think about the amount of data and information that we're taking in all the time, even just our visual system, it's such a high bandwidth of information that we actually don't take it all in at once. And I think that you can do this just experimentally by trying to expand your purview versus trying to be very focused and soda straw, if you will, which also can kind of loop into how we process and handle signals. I think that's very interesting. You also mentioned the brain as a computer, which I think a lot of people understand intuitively. One thing that I just came across fairly recently is that the first time that the word computer was used was actually to reference humans who performed calculations dating back to the early 17th century, which you wouldn't expect, at least I wouldn't expect. But I think that's very, very fascinating.
Mm-hmm. Yeah, that's right. Now we have computer machines, I guess. But yeah, computer was an occupation, I guess. One computes.
And one thing also that a friend and I were talking about over some beers last year, admittedly, I think that we were near graduation, so we were kind of going to our final send-off. He kind of blew my mind. He opened my eyes to the fact that the neural complexity of a human is actually a gradient. So it increases as you move upwards. Think of your hands or your body just having nerve cells communicating over to your spinal cord that works all the way up to your body to the hindbrain, which is essentially things that you don't even think about, like heartbeats, breathing, all these things. A little bit more internally, the midbrain, you have memory, things that help with circadian rhythm, like your hypothalamus. I think I'm getting those right. Don't correct me if I'm not. And then there's the outer brain, which then we get very much more complex things, communication, language, logic, et cetera, et cetera. Right. If we're trying to really model the brain and understand the brain with algorithms, how are we doing that in terms of techniques? Because that seems very, very complex and difficult to model in one shot. Are we trying to compartmentalize these things, or are we taking a very much a simplified approach to these?
So each of those different areas of the brain that you sort of the evolutionary layering of the brain that you sort of referenced, the different, I don't know a huge amount about the older parts of the brain, so the reptilian brain. They might have like a different set of algorithms that work there. Kind of where I'm more focused, and I guess a lot of neuroscientific research is focused, is on the cortex or neocortex. So that's the last layer of the brain. If you look at a brain, it's the noodly outer layer, the cortex. Now, it seems to be sort of the most recent evolutionary add-on, and it seems to do a lot of the highest processing, or sort of highest, most intelligent processing, I guess you could say. So when we have, when you're looking at something and you're like, what is that? Like, this is like, I don't know, like, okay, it's long, and you start to recognize it. Oh, it's an Apple Pencil. That's sort of that inference of taking the visual input and establishing or sort of reconciling that with some other memory that I have happens in the cortex. And there are areas of the cortex that are specialized to recognizing very specialized objects. And there's a part that in your brain that seems specialized for recognizing faces too. And a lot of the really high level executive type processing also happens in the cortex. Like if you see a donut on a coffee table somewhere, maybe in the office, you might think, wow, that looks really yummy, I'm just going to eat it. But then you think, oh, like your prefrontal cortex says, like, wait a minute, it might belong to someone. And this is where we get into the whole social dynamics thing, right? Like if I eat it, Janice is going to be really mad at me because she's known to bring donuts. And so maybe I should leave it there. And sort of like executive functioning, that's all cortex. And a lot of the mental gymnastics we do, like a language and mathematics and logic, and these all seem to be functions of the cortex. Something that all mammals have a cortex, but lower animals don't really have this. I'm not sure actually where the cortex stops, but they certainly don't have a cortex like we have. And there's fairly good correlation between how much cortex you have, how many neurons you have in your cortex, and how what we would call intelligent you are. Not you as a human, let's say, but as a species. Different species have different numbers of neurons in their cortices, and it to some extent correlates with what we would recognize as intelligence.
Off the top of your head, do you know of any animals that are
that have more?
Yeah.
I believe some porpoises or dolphins actually have more neurons in their cortex than humans, which is a little disconcerting because maybe it's just a language barrier. Like, who knows? Who knows what's going on in their heads? I suppose there are people who study them and study the sort of cognitive neuroscience of bottlenose dolphins or whatever. I'm not sure exactly what species it is, to be honest. But it'd be really interesting if we could sort of find out in a way that's not limited by language what's going on in their minds. Like they certainly seem to play. A lot of the social species and species that have bigger cortices seem to play. Apes, like the great apes, like chimpanzees and orangutans and gorillas, they're actually not very far from us genetically. We do have larger brains than them, like significantly larger, but they, as far as mammals go, they have pretty large brains too. And so they are many of those species are highly social and so exhibit the types of behaviors that we would recognize: aggression and guilt and loyalty and all these different things.
That is incredibly interesting and also a little disconcerting. As you said, even animals that we would think are very simple, such as crows, have been seen. I think a few years ago there was an example of a crow using pebbles to drop into a water bottle to raise the water level, such that they could then get a drink out of the bottle. So it's just when you think about these kind of things, it is very, very, as you said, disconcerting. Have we attempted to model brains of minor animals, for lack of a better term, these animals whose neocortexes are significantly smaller than humans? If we were able to simulate a human brain, that would be remarkable. But scaling that down, has there been any attempts at doing that? Any successful attempts?
Successful. I don't know about that, but there have been attempts. Depends what you call success, I guess.
Fair.
I mean, there are a number of species for which we know the entire nervous system. Like there's some worm that we know, like flatworm. It has like, I'm not sure if it's the right species, but there's some species that has like 304 neurons. Every individual has 304. They're all in the same position. They all have the same connections, and so it's not really a brain per se. It's just kind of like a nervous system that moves information around, and it's essentially a system of reflexes, I guess. That's not to say it can't learn or adjust. So there are a number of species that they're trying to sort of map out their entire connectome. Connectome being the word that represents how all the neurons are connected to each other. There's the Allen Brain Project, which they're doing high resolution tomographic imaging, basically slicing images of a rat's or I think a mouse brain, trying to basically put it together and kind of get I mean, the mouse has way more neurons than that flatworm. I'm not sure how many, but probably in the millions. So I don't know where that project is really, but there's basically an online database available. I think it's freely available. Certainly, if you're a researcher, you can get access to it, and you can start trying to sort it out. But it's kind of tricky, like starting from the anatomy, working your way towards how does it work. That's kind of it's not easy. So you can start. Let's say you've got some anatomy. You say, oh, these neurons are connected to these ones, and I've got this little circuit. I can run it. Maybe I can simulate it. What does it mean? That's still up in the air. Like there are lots of experiments where neuroscientists put probes inside an active animal's brain, and you can listen to these neurons firing spikes, and they can make the rats go through mazes that actually is a thing, and listen to the neurons in the rat's brain as it's navigating through this maze, and a lot has been learned about how the brain works and what different parts of the brain represent different types of information and how reward signals are handled. And so those experiments are good for that. All sorts of animals, birds and dragonflies and slugs and kind of cats and monkeys and all sorts of things. Yeah, I don't know if I've answered your question or not, but I certainly talked on for a while.
Yeah. So that sounds like very much empirical studies. They're taking the animals, they're inserting the probes, they're monkeying around, trying to figure out how this thing works. When they take that data back and they start to try to play around with that and make software models, have there been any successes with that? Have they been able to predict how an agent may respond through changes in their neural pathways or things like that?
Yes. So I guess a common thing that's said is neuroscience is data rich and theory poor. So there's lots of data. We've listened to lots of neurons. There are lots of neurons there. They're all firing, doing crazy things, including some amazing technologies where you can actually, genetically engineer these mice that when their neurons fire, they actually light up. So you actually put a camera. You put a little hole in their skull and put a camera on the surface of their brain and look for these flashing lights. And so from that, you can sort of get some idea of what neurons are firing when, according to what stimulus. But it's still pretty hard to come up with a theory for what's going on there. Like what algorithm is this part of the brain actually implementing? So what we do here at Waterloo is I'm a part of the Center for Theoretical Neuroscience. So theoretical neuroscience, like I said, neuroscience is data rich, theory poor. So there's lots of data out there. We need people who can come up with theories and basically say, well, maybe this is happening. Build a model, like simulate a neural circuit and design it so that it kind of reproduces the neuroscientific observations. Then that's a model. I mean, it's that then gives. It's essentially a scientific hypothesis. So you can say, okay, if my model is correct, if my hypothesis is correct, then we can come up with an experiment, whether it's correct or not. If I have a hypothesis, we can come up with an experiment that would test that hypothesis. So maybe if we give the neural circuit this different input, we would expect, running our simulation, we would expect to see this behavior. So that, at least in principle, you could actually take into the wet lab and say, okay, let's try that. Let's give this mouse or rat or dragonfly or whatever this slightly different stimulus and see if its behavior matches the model. So that's theoretical neuroscience, coming up with theories for what the circuits might be doing, building those circuits just in computer programs. And at Waterloo, we do have neuroscience here, but basically we sort of produce our theories, and if people want to try them, they can, or challenge them in the lab.
So taking that down from the abstract into an actual example, what is something that you have been working on to form a hypothesis that is then tested? For example, could it be something in regards to how agents learn in their environment, or how certain incentives or rewards influence mice, or things like that?
Yeah, I don't think I would claim that I personally have worked on the theory that's been translated into the wet lab and tested. I don't know if I can actually think of an example, to be honest. I'm sure there are some. I don't know if I can produce one.
No worries. Is there anything that is maybe outside of your lab, but still in the domain, that comes to mind when you think of the last 5 years or so? Things that have shooken out of this theoretical neuroscience field?
I guess something that's kind of interesting is the reward circuits, and its link to reinforcement learning. Now, there's lots of information about parts of the brain, the dorsolateral prefrontal cortex, and other parts of the brain that seem to process reward signals. So reward in the sense of maybe you're trying to score a goal and you kick the ball just right and it goes in the goal, and you actually feel a bit of euphoria, right? And that's the feeling of your brain getting dopamine. Because when you achieve the goal that you're trying to do, your brain recognizes that achievement and you get dopamine. As it feels like a reward, but it's actually just a chemical in your brain that is the currency of desired behavior, I guess. And so there's a lot known about the sort of reward signals, and things like when someone gets a reward, or when they do this action, they get a reward. At first, they get the dopamine hit when they receive the reward. But after time, it's the action that they take that leads to the reward. Once they take that action, they get the reward. Like the reward signal works back once you recognize the chain of events that will lead to reward. You get the reward when you recognize and start implementing that chain of actions. So this looks a lot like that. So that's been around. That sort of has been understood for tens of years. But more like reinforcement learning is something that's kind of really come into the forefront of computer science and engineering and science in the last, I would say, 10 years. And so the link between reinforcement learning essentially offers an explanation for or a theory for what's going on, what the brain is actually doing. Because I don't know if you or your listeners know much about reinforcement learning, but it's basically an exercise of, based on, you have this task to do, and you have some agent that's kind of trying different things and trying to achieve the task. And when they achieve the task, they get reward, like some numbers or something in your computer simulation. And so as it's trying different things, some actions lead to reward. And when it does an action that leads to reward, the current reinforcement learning algorithms have a way of sort of back projecting that reward signal into the actions and into the different states that are kind of leading up to the reward. So it's kind of a theory that goes nicely with the observations of the dopaminergic reward system. So I guess I'm not really sure what experiments have been done, but it seems pretty ripe. I'm sure people have been doing experiments essentially testing the reinforcement learning approach and reinforcement learning algorithms to the human brain. I mean, there's sort of a family of reinforcement learning algorithms of sort of different complexity. Wouldn't it be kind of cool to find out which one our brains use? I mean, that's I sure hope someone's looking into that.
Is that something that you would consider to be almost like a fundamental key of humans? Is how we most greatly are rewarded for taking an action? Then how can we exploit that? Not to jump right to the end there, but for example, if somebody is having issues losing weight, if they could somehow hijack their dopamine system to then be rewarded not by the post-workout meal or shake or whatever it is, but to actually work that down into the trigger of putting on your shoes, getting to the gym, working out, things like that.
Yeah, I think it's central. Like explaining, like having an explanation for why we choose the things that we choose to do. What could be more central to your being? So, like a causal link between stimulus and action, I think is kind of the holy grail. And I think reinforcement learning is kind of the direction to go. It's not, to be honest, it's not really central to my research field, but it really interests me, at least from a scientific, not necessarily research perspective. And it's huge. Like here we are talking to each other. Like why? Why are we talking? Why do you have a podcast? Somehow you get reward. Your brain sort of rewards you for it. Now, maybe you don't get rewarded when you, are editing the podcast itself, because that seems like work. Maybe you don't get rewarded when you're trying to schedule things, but maybe you feel reward when you publish it and you see it online, and someone contacts you and says, "Hey, I really like this thing, and gave me these ideas." Why do I do my job? I think this is kind of key. So you went through engineering. Was that easy? I don't think so. Hard.
Right? It was hard.
It's hard. I mean, lots of different things are hard. Going to university in general is hard. So why did I go to study math? And thinking back to high school, what was it about math that sort of clicked with me? Like, why did I think that was actually kind of fun, solving those problems? And it's all got to do with reward system. And, some people like math, some people don't. And I think that tends to translate into, this person is good at math, this person is not. What it really means is this person can tolerate or they feel reward when they do math. This person maybe doesn't get such a big bang. So that drives how we decide to spend our time, what thoughts we decide to entertain, and really, what you become expert at. And so something as small as that can have a huge influence on your life. And everything we do, this is being played out. These decisions are being made. These choices are being made 24/7. So, and it's all, arguably has to do with, it's dopamine and how you choose what you do, and the reinforcement learning, reward signals, addiction too. So some people, some drugs basically hijack your reward system. So then life revolves around not doing the things that you and I have been talking about, the sort of, let's say, wholesome things that you could say math hijacked my reward system, but I'd like to think it's been useful, not just to me, but to other people, kind of been constructive. But there are, I guess, non-constructive things that do give you big reward, like doing cocaine or whatever, ecstasy. And if the problem with drugs is that it hijacks the reward system, and suddenly all your actions are towards one specific goal, is to get more of that drug. But it's an interesting perspective, right? If you put it in terms of reinforcement learning, I think you can train reinforcement learning algorithms that if you give it this easy out where it can get lots and lots of reward, but by doing something that maybe in some broader scope is actually destructive, it'll get sort of distracted and keep doing that thing.
Oh man, there are so many ways where we can take this conversation from here. That was beautiful. I think a few points there. So I think some people might be listening and hear, "Oh, you got rewarded for doing math? That sounds crazy." But I would argue that you can almost set yourself little micro goals, right? And like once you achieve a micro goal, say, problem set 4, problems 8 through 9 are really challenging. If you can push yourself to really sit down and work your way through it, whereas other people don't. You show up to school tomorrow and you're the one of 5 people out of your class who's got this problem done. You might get a massive reinforcement signal from that. And that might be enough to propel you towards a path to study mathematics. I think that is so interesting and so fascinating. Which also the inverse of that is, say you're in school as a young child and you get discouraged or you find yourself not able to do certain kinds of problems or be involved in certain spaces. That discouragement might just shut that door for you entirely, which, I mean, not all at once, of course, but you go through this path once, twice, 3 times, all of a sudden your neurons are now aligning to light up in a certain way, and that might deteriorate your ability to then perform in that avenue, which I think is very, very interesting. How much of this, in your opinion, is different wiring for just different people? As you said, some people just don't like math. Some people love it. How much of this is nature versus nurture? If you're aware or can make any guesses. Pretty speculative question. Don't feel pressured to answer. We can.
That's a good question. I mean, without knowing much. Well, I guess there was a book published by Steven Pinker. Mm-hmm. I don't know if your listeners have heard of him. I love Steven Pinker. He writes really big fat books, but he just makes so much sense. He's from Montreal. He's Canadian, but he's a psychologist. I think he's in psychology at Harvard, if I'm not mistaken.
He being famous for having this eternally optimistic view of humanity now is the best time to live ever, and et cetera, et cetera. Just some background.
To some infamous for that, but I read that book and I mean it has data, so I'm not. I think he's well researched, but he's written other books. One I'm thinking of is called The Blank Slate. You were talking about one called The Better Angels of Our...
Something like that, yes.
The Blank Slate, he wrote a book years ago a few years ago. Basically, like the idea of the blank slate or the tabula rasa is that we're all born the same, and how we develop is purely a result of environment. But he's basically saying that's not the case. And he has all sorts of like data from like identical twin studies and longitudinal studies of human behavior and other animals that basically says that a large part of who you are and who you become has to do with stuff that you inherit. So I don't remember the specific numbers, but it's let's just say 50-50. About half of your behavior is explainable from your genetics, and half is explainable from your environment. So I mean, you can sort of drill down. It's not my field, so I don't know all the statistics, but I expect that there are sort of differences in certain behaviors, but those behaviors are probably not necessarily immediately what you would recognize as a behavior. They might be more like tendencies. Maybe tendencies is a better word. So for like we were talking about enjoying the feeling of solving a math problem. That the enjoyment of that is kind of a tendency, right? It doesn't make you good at math, but that makes you more likely to do more of it. Or some people, I mean, there could be differences in the way people's brains are wired, I suppose. Maybe some people are just naturally better wired for physical activity. I'm not making that claim. I'm just saying maybe. I don't know. It seems to be both. It seems to be a significant amount from both.
Great point there, being people who may have a tendency to be hooked on drugs, have this addictive personality kind of phenotype. Maybe if they were just directed a different way, they could have a vastly different outcome if they were instead rewired to be on a track of societally positive work that's rewarding and fulfilling. That might be enough to change
Addiction
course.
seems to have a fairly significant genetic component.
Interesting. Very interesting. I want to kind of switch gears a little bit. Let's get away from more of the speculative stuff. On your website, you have a quote, which is, "The ultimate goal of mine is to find something akin to the theory of evolution for the brain." So we've kind of been dancing around this a little bit. Is there more to that than this reinforcement learning mechanism? And if so, can you just explain what that means and what it means to you?
Yeah, sure. Ever since, I guess, my undergrad, I've been interested in the theory of evolution. And what I like about the theory of evolution, it's kind of the same thing I like about neuroscience, is that it's this super simple idea that things are competing, there's sort of genetic diversity, and as they compete, the things that are, for whatever reason, slightly better tend to, have more offspring, and that produces genetic change in the population. And just on that simple idea, you get this entire bush of different, like diversification of different living things that explain really all the complexity that we see. So it's a simple rule, but used over and over and over again that generates all this complexity. So I guess the hope for theoretical neuroscience is that there's something like the theory of evolution, or something like the theory of how would they say it, like survival of the fittest, or that sort of idea in the brain. Not that they're competing and they're surviving or not competing. It's not the same theory, I'm saying, but it'd be nice to find a simple set of rules that dictate how the neurons grow or behave in your brain. That the simple set of rules is easy to understand, but when it's being implemented over like 80 billion neurons, or let's just say 16 billion neurons of your cortex, that creates huge amount of complexity. So there's some hints that it's hard to tell how simple the theories are, but the holy grail is that that there be something fairly easy to understand, and it only becomes complex because it's being used in such a large scale.
Because we're focusing on the neocortex, stuff that isn't just essential for the operating system of humans to keep working, is this all around learning then? Like being able to rewire the brain to do certain things? Is that kind of in the domain of what we're talking about, this theory of evolution for the brain?
Yep, but learning, a newborn baby just sitting there looking around is also learning. It's changing its network connection weights to sort of extract statistically salient aspects of the visual scene. Same with audition, like hearing. So learning across the brain, not just learning like, let's go to school and I'm going to learn how to, like, the algorithm for doing 2-digit multiplication. Like, most people, when you say learning, they're thinking about going to school and being taught different ways of thinking. But learning is much deeper than that. Learning to walk. How do you learn to walk? Well, it's kind of like reinforcement learning. Basically, you try things and it doesn't work at first, but you might take of course, you don't remember learning to walk, but that doesn't mean these processes weren't happening in your brain. Take a few steps. Hey, that worked. And some part of your brain recognized that was a successful run and sort of tries to duplicate those behaviors. Balance and motor control and all these sort of very deep processes also learned. But then as you grow older, it kind of turns into, maybe you're like me when you're in first year and you took calculus, it's like seemed really hard. Now that you've graduated, maybe, I don't know about you, but I look back at calculus and think, like it's not hard. But that's because I've been living and breathing it for many years. So I've learned it. Like my brain now can sort of represent those ideas more efficiently. And same would be true for lots of things. Like engineers will have their own field of expertise. People who are, let's say, professional dancers, like like certain dance moves, it would take me ages to try to figure out how to move my body like that, and yet they can just do it because they've learned.
So you tell me that there's no ballet shoes in your closet behind you, Jeff? Is that what you're saying?
No.
We've spoken a lot about reinforcement learning. Is this the leading theory or domain for something that would be tangible from a theory of evolution for the brain, or are we just trying to mimic what we see in humans? And is there something that you suspect is fundamentally much more simplistic, like the theory of evolution, as you had mentioned? I guess it is pretty simplistic.
Reinforcement learning?
I mean, not to implement, but the concept of it. Actions that lead to dopamine hits are reinforced and then acted upon. But are there other competing streams?
So one thing that interests me right now, and this seems to be a theory that's getting some traction, is what's called the free energy principle, or it's related to predictive coding. So like a lot of the vision models, like I'm thinking back, like this field of neural networks moves so quickly. So every time I say something, I'm worried like tomorrow it's going to be just completely bogus. And but a lot of the vision models are sort of like feed forward. You give the image input and it says, oh, it's a cat or it's a dog, or, it has certain things that it identifies in the image. So we're really good at designing algorithms like that, or neural networks like that. When I say we, I mean not necessarily me, but other people with big computers. And but the brain doesn't work that way. The brain takes information through your eyeballs, and then, yes, information flows up through, I guess you could say, a few layers of a hierarchy of understanding, sort of layers of transformations of the information, let's say. The goal is to sort of turn that very concrete information, like pixels that go into your eyeballs, turn that into useful information like objects and things moving and edges and stuff like that. Because in real life, objects don't really exist. Everything's just a collection of particles, right? So objects don't really exist. We recognize things as objects. We classify them. Objects are human-made concepts. In reality, everything's just particles moving around. But we think of things as objects because it's helpful for us. It's got a lot of utility to think of things that way. So anyway, we have our brain, and we sort of abstract these sort of hierarchical representations into something that's useful. But at the same time, our brains send information in the opposite direction too, saying like, okay, I think I'm looking at an Apple Pencil. Now, if I am looking at an Apple Pencil, then this is what the layers below me should be experiencing. And so there's this sort of back and forth conversation between the sort of lower sensory parts of your brain and the higher, sort of the cognitively higher parts of the brain, maybe the association areas that one side speaks in language of like pixels, let's say, or maybe little tiny edges pieces. Other side speaks in language of objects. And the mapping between them takes a few different layers of sort of unpacking or reconfiguring. So when you look at, let's say you saw a photo of an Apple Pencil, but it was really noisy, like really grainy, maybe it was taken in low light or something like that.
White background, can't really make out the edges, things that it's like a little more obscured.
Yeah. So you'd look at that and you'd be like, what is that? And it might take a minute, but the theory is basically that your brain is, but the sensory stuff's going in, and the upper layer hasn't quite nailed it down. It's like, I don't know. I mean, it could be lots of different things. And then that upper part of your brain is coming up with theories like maybe it's a jaguar, maybe it's an apple, maybe it's apple's a bad example because it's an Apple Pencil. I meant apple that you eat. And eventually, like you try to stumble upon a theory in your mind that explains the data. And when you get it, it's like, aha, yeah, it's an Apple Pencil. I see it now. Or maybe you don't see it, but your friend sees it and they say, oh, it's an Apple Pencil. And you're like, oh, yeah. That feeling, that aha feeling, as the theory goes, is the network settling to suddenly coming up with a solution that has a low energy network state. You could there are ways of representing how much energy, how much tension or disagreement there is in the network. You've got this input, you've got a theory of what it is. If they don't match very well, there's still a lot of tension in the network, like the information is going both ways and they're not quite matching. But once it's Apple Pencil, suddenly the network settles into like a stable, low energy state.
That's interesting. That's because so what comes to mind is, let's take a evolutionary perspective on that. If your brain can't make out what it's looking at, is it a snake or is it a stick? There's incentive for your brain to be on high alert and be anxious or uncertain about what's in its environment. So is that perhaps kind of what's being tapped into there?
Well, there are kind of two different passes. So there's the gist pass, which is first of all, there are different parts of the visual stream. I'm talking about the cortical visual stream. So it goes into your eyeballs, goes to the back of your brain, the primary visual cortex, and then works its way through the cortical visual areas. There's another stream I'll just mention briefly that goes into your superior colliculus or something. It's an old part of the brain. It's one of the I don't know if it's midbrain or I'm not sure what part of the brain it is, to be honest. But it seems to have some circuits that hard code. I don't know if hard code's the right word, but it learns or it reacts very quickly, very efficiently to threats that it recognizes. So you're walking along, you see something, maybe it's a stick, but it looks like a snake, and before your cortex is even processing it, your superior colliculus has basically made you jump and get away from it. And so there are a number of different things. I think probably spiders maybe fit that as well. So the number of different stimuli that are almost like reflexes.
Yeah, even surprise, like say I'm taking a walk downtown Austin, it's late at night, it's dark, and I walk by somebody who's maybe on their phone and they're not paying attention. They have this jolt of surprise. Oh my God, am I in danger? Like who's coming up behind me? And then when they realize maybe I'm smiling or something, I don't know.
Yeah.
And their brain says, okay, no threat, maybe settle in and don't need to worry about anything.
Yeah, and there's a startle reflex that's specifically for vision, where it recognizes some very rudimentary templates. Now, I don't know much about that, but anyway, so that's one part of your visual system. The part I was talking about, now I'm trying to remember how I got on that tangent.
Trying to make sense of objects in the world you see, an Apple Pencil, maybe it's not quite clear or whatnot, and your brain has this disagreement.
Yeah, so there's this gist perception where there's the superior colliculus. That I'm not talking about that. Even in your cortex, you kind of have this initial flow of information where you, let's say in the first 100 milliseconds that you're looking at something, you kind of form a perception of it. Now that perception may not be accurate, like optical illusions are all over the place. And the continued sort of back and forth negotiation between your different layers, that kind of adjusts the gist to a more, a better, more fundamentally grounded perception. But the gist is still powerful, and sometimes you don't even know what the actual answer is, and so you kind of tend to go with what the gist is. And maybe that's kind of behind what, like, people see faces all over the place. And if you see a face in the clouds, you'll be, wow, oh, but you know it's a cloud. So you can sort of, after the gist perception, you can sort of reason that, oh, it's a cloud. There aren't huge people in the sky with faces looking down. But sometimes you can't necessarily explain that. And so if you go back in human history, like a few hundred years ago, where we had less explainability of things, people would basically assign agency in the sense of it's an agent, it's a person like thing that's acting on its own behalf with some rationale. So people are kind of hyper sensitive to observing things with agency. So when you're programming and the program's not working properly, You might be like, screw you, computer, what the hell's wrong with you? Why are you doing this to me? Like, you're treating it like it's a person. That's because that's a very natural way for our brain to work.
Very interesting, this tie back of looking for faces, for social kind of cues, even going to the neocortex, as we said at the very beginning of this podcast, which is your brain has developed because of these social pressures. You want to be well adapted to pick these out and parse these. I guess this kind of leads us to my next question, which is, okay, sure, we can nail down the technical abilities of us to learn and all this, but what about the elephant in the room? What about consciousness? And if you could just maybe explain a little bit about what consciousness is, because I feel like for everyone that's not a very clear concept, and then we can maybe talk about how this relates to learning about the brain for a fundamental theory or so on.
So that's pretty loaded. Like, what is consciousness?
My apologies.
Nobody has a really good answer for that. And yet everyone has an answer for that, because consciousness is what I feel when I'm thinking about what it feels like to be conscious. So everyone knows what it feels like to be conscious. I don't know. Do we know what it feels like to not be conscious? I mean, I guess maybe not. I don't know. It's an interesting question, but I mean, there are different approaches to consciousness. There are some easier to nail down facets to the problem of consciousness, to the question. So you can say, like, consciousness could be, are you consciously aware of something? So you can do different experiments where someone's watching a screen and bloop, there's a quick flash, and maybe the flash is so fast that they were not consciously aware that they even saw anything. So did that image enter their consciousness? I think you would say no. If they report no, then to a large extent, what we consider consciousness is what we are able to report. So if you ask them, if you choose to use like language as the reporting mechanism, they would say, no, I didn't see anything. Like, don't know what you're talking about. And yet, you can do experiments. Now, I don't know the nuances of all these, but there are different really clever experiments where you do some sort of flash. The person reports that they didn't see anything, and yet you can ask them questions afterwards or do some sort of task, and you can show consistently that what they saw influences their behavior afterwards. So maybe the really quick blip is actually an arrow pointing one way or the other. And they have to choose one side of the screen or the other. And as far as they're concerned, it's just random. It's like, I don't know, I'm just that one, I don't know. And yet with better than random probability, they'll choose the one that the arrow pointed at, even though they were not aware of the arrow. So I don't know if that specific experiment was done, but there are experiments like that show even if if you're not consciously aware in the sense that you can report it verbally, it still can influence your behavior. So in that sense, you're conscious on some level of it. So, I mean, where is consciousness? Where does consciousness end? Like, is something influencing your behavior? Is that conscious? I don't know.
Yeah, these are all fascinating questions that I hope we can maybe learn one day what exactly this thing is. I mean, it's very hard to try to understand the system when you're within the system, as you pointed out, but it's very curious. A little bit of a stretch now, but AGI, so artificial general intelligence, this has been getting a lot of buzz recently with some of these large language models that have been coming out, which we can touch on later. Can you just give a quick debrief for someone who's not aware of what this would be? I don't know how they would be not aware, but let's educate them. And then let's talk a little bit about consciousness and AGI.
Okay, so easy stuff. AGI, I mean, I guess the idea of AGI has been around for a while. Like, wow, wouldn't it be cool if we could make something that's not just good at identifying cats in images, or not just good at identifying sounds or something, whatever neural networks have been good at. what if we could have something that's sort of good at all of it? So that's kind of what humans are, right? Like, I mean, we model the idea of general intelligence after ourselves, which is a bit suspect, to be honest, because we think we're so smart, but actually, we have many, many cognitive mistakes that we make routinely. So we're not, I can easily imagine a better intelligence than us. But anyway, so we are the current best standard that we can think of. So we're thinking AGI is basically, can we make something that seems like it's a human intelligence to us? And I mean, it actually comes back to the Turing test. Alan Turing, the famous guy who did all sorts of cool things like the Enigma project, or I guess he broke the Enigma code, or was up on the team that did it. He actually did some really interesting stuff with pattern formation, that like cheetahs and shells and like different sort of biological patterns. There's a thing that he's got. There's a Turing thing. I can't remember. It's in my master's thesis. But he also came up with the Turing test. So basically, if there's artificial intelligence, how would you test it? Like, you could give it math tests and things like that. But his idea was, let's say you're just on a computer and you're typing questions and you're communicating with this. Let's say you're communicating with this thing. You don't know if it's a person or an AGI. So if through a bunch of question and answers, the person is convinced they're talking to a person, or messaging a person, that is passing the Turing test. So if a machine or an AGI can pass the Turing test, that for a long time was considered the standard for intelligence.
Ex Machina being a fantastic movie that dictates this and shows this with a humanoid robot, but you can just abstract the physical interpretation, just have, say, a software device and an interface like that, and it gets wild. If anyone has not seen that, watch that movie. It's fantastic. Sorry, Jeff, continue.
Interesting. A lot of the robotics, sort of the motor control, is kind of the hard part now. I mean, AGI is hard too, but really that degree of robotics is not easy. It's not my field, but I know I've been told it's extremely hard problem to make something like just something so simple like this, like tapping on my phone or whatever, putting my glasses on. Like, it seems so easy, but it's really hard to get a robot to do that. But anyway, so now we're into these things are moving so quickly. Like, just a few months ago, ChatGPT came out, which stands for Chat Generative Pre-trained. So they take these pre-trained language models and they sort of tune them to be even better at this particular problem. So, I mean, you can sort of talk about it like, oh, it's just predicting. Like, really, it's based on just predicting words. So as words are coming out of it, it's predicting the next thing it's going to say or type, right? Like you probably had a few words in mind predicting what I was going to say, and so we're always we're predicting what the other people are going to say all the time. It's kind of one of the things that the brain seems to do. So this ChatGPT, its mission in terms of how it was trained is to predict what the next word is going to be. So it was given all sorts of sequences of like sentences and like billions of sentences, and its job was, okay, given these 18 words, what's the next word? And I mean, you would think that's really stupid, like predicting the next word, that's not intelligence. But I think what we're seeing is that predicting the next word can actually be done a lot better if you have a very rich model of how the world works and what the world does, and information and relationships, and like to sort of accurately predict the next word, you actually have to have a lot of knowledge and a pretty rich world model.
Absolutely, yeah. And think of the last 30 years of internet use, pretty much scraping all the conversations, all these articles, text, even images now. I believe one of the core things that stood out to me when they demoed GPT-4, which is the latest iteration of ChatGPT, was they show it a picture of a little girl holding balloons. So you've got a little girl with all these strings clenched in her fist, and there's clear tension pulling the balloons upwards. Let's say that they're helium balloons, and they feed the image plus a prompt saying, "What would happen if I cut the strings?" And it says the balloons would fly away. Which that if that doesn't blow your mind, I don't think that you understand quite what's happening. It's analyzing the photo. It understands how each object in the photo is related to one another and how it physically reacts in the world. And it can predict, it can use logic to determine what happens if you were to do something to modify the photo. Yeah. For a machine, this is incredible.
So, I mean, one could argue that somewhere on the internet that sentence exists. Maybe, but I mean, I don't think the model has enough parameters to encode every utterance that it's seen. It does, like, it has billions of, depending on which, I know you said ChatGPT-4, I don't know how many parameters it has, but we're talking about billions of parameters usually in these large language models. That's not enough to encode every text utterance on the internet. So there has to be essentially some compression of all that stuff into a more meaningful, more useful, more abstract representation. And so I guess that's just a demonstration. And maybe that's just what our brains are. Like, maybe our brains are essentially a compressed version of all of our experiences, but it's compressed in a way that we can sort of generalize, and we can basically extrapolate or extract generalizations of how the world works. They say if you have a perfect memory, your life is hard because you need to forget stuff, so that what remains is the sort of general properties of the world, sort of the general patterns, not the specific details of each episode.
So you can continue with your life even after you blunder the Little League game when you were 10 and you lost it for your team. You can still recover and move into the world in a meaningful way.
Yeah, I'm sorry if that happened to you.
It wasn't baseball, it was soccer, but it's okay.
Well, I played one season of hockey as like a, I don't know, 6-year-old, and I scored on my own net. So I gave up the hockey at that point.
Jeff, you just got to forget. You got to let it go. It's all right.
I'm still a good person.
This is very interesting. So we've created these remarkable technologies, these large language models, LLMs, which are now popping up all over the place. You have OpenAI, which is ChatGPT. Facebook, I think, has one called Llama. Google's got Bard and other ones. Minerva, I believe, is one that's more math focused. And as you mentioned, you don't know how many parameters ChatGPT is trained on. They actually aren't releasing that to the public because now this is something that is deemed as confidential information or proprietary information to their product, which is also very, very fascinating. So it feels like we are on the cusp of something, even though I've heard from many very, very well-respected researchers that AGI is something that we are far, far, far away from. My question is, and now I guess looping this back to our little consciousness deviation, if an AGI is to truly be an AGI, do you feel like it needs to have some level of consciousness?
I guess it really depends on how you define consciousness. That's the answer to every question about consciousness. It depends on how you define it. Next question. I don't think consciousness is really well defined.
I suppose it's kind of an impossible question because I can only infer that you're conscious. I mean, you aren't here with me in this room, but we're having this conversation. I can reflect and think about your experiences and how you might be reacting to my words and how I can make you feel in this dialogue. But I can't really necessarily ensure that you are reciprocating and doing the same thing. Once you take this implication and you apply it to software, I suppose it's really truly impossible to deem.
I would guess that consciousness is probably related to the degree to which an organism needs to model its own agency in its environment. So every animal has to model its own agency, but for some animals, they just have to know if they're too hot or too cold, and that it needs to move over there, and avoid predators. Like it probably has some model that it needs to be aware of other agents. So in that, because the brain is, like I said before, it's basically about predicting. So animals are sort of predicting the what's going to happen if they do this, what's going to happen if they do that, and so in order to make those predictions, you have to have some concept of self. Now, that doesn't have to be a very deep concept of self. One of the sort of canonical tests of consciousness is the concept is looking into a mirror and do you recognize yourself as you, or do you think it's just some random person? And different animals can do this, some don't. I find it interesting that some cats don't care about mirrors, and some cats go berserk when they see it themselves in the mirror. So social species like us, like we talked about how it's a lot more complicated to operate in an environment where you have lots of other agents that are also operating in a complex environment and trying to cooperate and sometimes trying to take advantage of others. So we have to have our own concept of ourself in that system. And so I'm thinking about what I'm thinking. I'm thinking about what you're thinking. I'm thinking about what you're thinking about what I'm thinking. And this sort of recursive theory of mind, that might be kind of at the basis of what we think of as consciousness, sort of our own understanding of where we stand and how we relate to the things around us. We have a bunch of memories, and we can conjure up memories of different instances of where we were in relation to our surroundings and other agents who were around us, other people. So, I mean, apart from that, though, I mean, consciousness, apart from being like having a memory, or basically an identity, and a memory for us is at least is a big part of our identity, and being able to respond in a way that's sensible to other things around you. I mean, if you've ever had an experience where you don't remember everything that happened, you did go through university, so maybe you've experienced that. At the time you're conscious, but you have no memory of it afterwards. That's a weird feeling. Like it kind of isn't you, and yet you were conscious at the time in the sense of behaving, person. Anyway, I think the water's very muddy and about the consciousness question, so I'm just trying to dance around it, I guess.
No, that's quite all right. It's quite all right. I guess bringing this back to the concept of these major advancements, and I think I quoted 2050, I think has been a historic estimate for when AGI may arrive. As somebody in the field, do you have any horse in the race? Do you have any opinions when it comes to our path to this technology? Are we headed towards that, or do you believe that we need some kind of big black swan event to really change the way that we're approaching AGI?
So, I suggested that AGI is sort of modeled after human intelligence. And I also said that humans are not that intelligent, really. There are lots of ways that we make mistakes. So I don't think AGI is going to be the stopping point. I think it's just one milestone along the road, and maybe we're almost there. I mean, in different topic areas, people have different intelligences, right? There are even different dimensions to one's intelligence anyway. But so we're not all equal there. And I guess AGI is going to continue. I mean, I don't really know, but I'm thinking 2050 is too far in the future. I think what we're seeing with like GPT-4 and these things is like they basically pass the Turing test for many people. Maybe if you really know what you're doing and you get technical and you kind of know how to, but I guess that's the thing. Like, so in terms of passing the Turing test, if that's a measure of AGI, who are you comparing it to? Because people are stupid too. People make mistakes. People have false memories. People, aren't perfectly logical and rational. So in that sense, if you're sort of probing ChatGPT and you find it makes a mistake, well, how do you know you're not just talking to a person who made a mistake, or a person who's an idiot, or a person who's who's a real sociopath or a psychopath. Like I'm thinking of that thing where the Bing was trying to get that journalist to leave his wife, and
oh boy. Yeah, that was I believe that was Microsoft implementing a pre public release Chat GPT-4. I mean, I guess it was public, but what OpenAI has released seems to have more guardrails on it, which is also very interesting. The fact that they've applied these restrictions to what it can output. But yes, as you mentioned, Bing's AI went a little bit off the rails when it launched. I'm sure that they've cleaned that up now. I haven't really played around, but
people go off the rails too. And like, the commentary was like, well, what was this trained on? The internet? Yeah, of course. You see all sorts of crap on the internet. People being really arrogant and offensive, and I mean, there's lots of good stuff too, right? But in terms of where it's going, maybe you're sort of hinting at the singularity, and I know it's almost like the S word, right? Oh, the singularity,
Could you explain what that is for folks who aren't aware?
So the singularity is basically when artificial intelligence becomes so intelligent that it outpaces human intelligence. And I guess if artificial intelligence becomes smart enough, it'll be able to program itself even better than humans can program it. And so it'll just sort of take off intelligence-wise and leave us behind. At least that's my interpretation of the AI singularity. And so, I mean, it's always kind of been talked about like, oh, these robots, and like the movie The Terminator, these robots are going to basically become self-aware, realize they don't need humans, or they can basically use humans as slaves or something, and we're going to be slaves to these robots. That doesn't seem, partly because robots are hard to make, like I was saying before. A more likely version of the singularity is that AI is going to pump out so much information, and we're not going to know what information's true and real and what information's just confabulated or made up by AI. I mean, we already have that problem, and you could argue that that's largely human generated. But imagine if an artificial intelligence decides that it's in its own best interest. Well, I mean, it doesn't necessarily have motivations, but maybe it's being optimized for something, and it happens to be that the road to that optimization is to confuse humans into not knowing what's real and what's not.
Yeah, that point of reliance on the outputs, I think, is very interesting. There's been some studies, and I wish I had the data in front of me, but it was something like 96% of some sub-organization within a company fully believes and relies on the outputs of Chat GPT, or that they don't have any qualms about the answer, which I saw your eyes go wide, which is, it's a little scary.
I haven't used it much, but from what I've heard, it can very confidently say things that just are patently false. But people do that too. In fact, if you archive this, probably someday we'll look back at this conversation and be like, wow, Jeff was really full of shit on that topic. I can't believe they thought that was acceptable. Even though I believe it's true now. I believe everything I've said is more or less true. But I could be wrong, and I'll find that out later. What I think is like truly kind of scary is my master's student gave a presentation yesterday about he did a review research paper on reinforcement learning and these large language models. And he was sort of laying out how, yes, there's reinforcement learning, and traditionally, like, we generate the reward signals, and they're very sort of self-contained tasks. These like little cute little robots, not real robots, simulated robots moving around trying to find food. But these Chat GPT things, these are being trained by reinforcement learning too. So you get a bunch of humans that are basically, you give them maybe some AI generated, maybe there's a prompt like, tell me about such and such, and they'll two AI generated replies to that, and the human will choose which one they think is better. And just through millions of those, that's basically they are now training neural networks to try to learn to predict which one the human will find better. And they're going to use that neural network then to be the reward giver. And so they can start doing reinforcement learning all by itself. Take humans right out of the loop after that. So these chat optimizations can operate, like learn through reinforcement learning, generating their own rewards. That seems kind of unstable to me. So he mentioned this thing, and I haven't looked into it, called what's the word? Constitutional AI, where you want to sort of get this AI to sort of self-generate and self-learn, but you give it this constitution. These are the principles by which you must operate. And you've heard some AI rules like this before, like you can never harm a human, you can never do a thing that will result in a human being harmed. I don't know if that's it, but there's this set of principles by which these things can abide by, but continue learning. To me, that seems sketchy. I mean, we can't, as a species, I mean, between different countries, we can't even agree on what are good rules and what is a good constitution. Letting an AI engine loose, like you can give it a constitution, but as soon as you lay down some rules, you can game it, right? You can find loopholes, and I don't know. I don't think it'll take 2050 for us to be completely sort of overwhelmed with AI.
Yeah, there's recently been a public letter that's been going around. I'm sure that you've seen this, calling for the halting of any progress past the sophistication of Chat GPT-4. So no training models that are larger than GPT-4 for at least 6 months, so that people can gather and talk about how do they align AI to humans, which, as you just mentioned, what does that actually mean? Different cultures have different values, different nations have different values. And it's just, it just takes one. For me, this is one of the most concerning things that we are doing right now in terms of existential threats or uncapped downsides. I have friends who I've talked to who are just spiraling almost, which sounds bad, but it's a very serious thing. And I don't know that people are really understanding the magnitude of what is happening here.
Yeah. Like when social media first came out, I thought, this is great. I can contact my friends from high school. I totally did not see the downside, which seems to be its overwhelming impact. Basically creating divisive, bipolar politics and bipolar everything, right? Sort of drives people apart. So it's just another example of a little algorithm. Just it's got a very sort of singular goal, and yet it has this very complex rendering throughout society, very complex manifestation.
Yeah, it's scary. You don't know quite what's happening. So to have a constitutional AI that's going to reprimand the other AIs into complying with what humans believe to be a proper way to proceed it's concerning. But hey, let's end on a high note. What do you say, Jeff? Do you have any predictions about AI? Oh, what's that? Sorry?
We can at least enjoy the next 2 years before the AI overloads take over.
I mean, I'm in the States now. I'm not looking forward to the elections coming up. I think that is going to be absolute chaos. But hey, we'll see. That's my prediction.
Entertaining, although it has more impact than strictly entertainment for us here in Canada. But yes.
Absolutely, yeah. I don't know if you saw the fake or the AI photo of the Pope with the big white puffer on.
No.
I don't know if that means anything to you. You should, after this call, look it up.
Okay.
It's hilarious.
Yeah.
Is there anything in AI that you are specifically looking forward to or have your eye on for the near or mid future? I know that we've just been talking a lot about these LLMs and these ChatGPTs of the world, but are there other things that are maybe not in the public side that you think are perhaps interesting or important?
I guess there are a couple things. One is, and this could be considered a negative because it talks about making neural networks more efficient, but there's a push by many companies to make neuromorphic hardware. So right now, a lot of neural networks, basically GPU is kind of the computing engine of choice for doing neural networks. They're not really designed, GPUs, graphics processing units, are not really designed for that. They happen to be good, GPU manufacturers are now sort of generating GPUs that are sort of more amenable, more useful to neural network training and running. But so GPUs are power hungry, so they take a significant amount of electricity and they have to be cooled actively. And but I mean, your brain is running a neural network that's far bigger than models that we run, and it's using the same amount of electricity as one light bulb, and it's super fast. So neuromorphic hardware is basically trying to take kind of the philosophy of processing of the brain and put it on a chip. So basically, a whole bunch of very simple neurons operating in parallel, passing spikes between each other. So these platforms can run large neural networks at real time. I mean, this is the promise anyway. There are like prototypes and companies working on it, but it's not necessarily delivered to the masses yet. But not only large neural networks, but very low power, like a fraction of the amount of power that is used by a GPU, let's say. So that's kind of exciting. And some of the algorithms I work on are sort of designed or targeted towards neuromorphic platforms.
I find that very interesting to draw the comparison to the new Apple laptops. So Apple, for those who are unaware, they switched over from Intel's i chips, which are essentially a standard piece of hardware that Apple then takes and can program. However, when they built their own hardware, their own silicon, they're able to customize the layout to most optimize their computers. And if you look at the jump in battery life, performance, almost every metric from the Intel chips to the M1s, which were, I believe, 3 or 4 years ago at this point, it was almost a discontinuous jump. So it was a massive, massive climb. If that can be replicated for neural networks and AI, that is, again, very hopeful and also maybe a little scary too.
To be clear, we're talking order of magnitude. We're not talking like a big jump. We're talking orders of magnitude of efficiency. The other thing I'd just quickly mention is it's been around for a couple decades, but brain-machine interfaces. So, kind of probing into the brain and listening to different neurons spiking and stuff. In different regions of the brain, we can decode what those spikes mean. So if the classic example is they put a probe in a monkey's motor cortex and listen to the spikes as it was reaching and doing some task. And after a while, they could predict how the monkey was going to reach just by listening to the neurons. And this was decades ago, or at least a decade ago. And so I think there's a lot of potential in probing information directly out of the human brain. I know Elon Musk has his Neuralink thing. I don't know if that was strictly surface of the scalp, but anyway, if you can get into the brain and probe into the cortex, into actual neurons, you can get really good information. And they've done experiments where you can bypass a severed spinal cord, and maybe not for the whole body, but you can still control an arm directly from the brain, basically fill in the missing nerves and drive the arm. So I think there's a lot of promise there too. It's kind of an interesting, now that opens up this whole can of worms. So you can also feed information into the brain, and the brain can actually learn to interpret impulses that are sent in from a computer. So, what then? It'll be interesting to see where that goes.
Profound impacts for people who suffer with disabilities to maybe regain some life. And then beyond that, who knows, Jeff, are we going to be entering the matrix? I don't know. We will see. Jeff Orchard, ladies and gentlemen. Jeff, if people want to follow your work or keep up with you, where can they go? Social media, website, etc.
Usually, there aren't that many Jeff Orchard. So if you Google Jeff Orchard Waterloo, let's say, which should probably be me. But you can also just go to the University of Waterloo webpage. I'm in the computer science school, the David R. Cheriton School of Computer Science. And I got a webpage there, and I've got a lab called the Neurocognitive Computing Lab with lots of talented grad students and postdocs.
Jeff, thank you so much for your time. Really appreciate it.
Thanks, Jack. It was fun.